Okay, so now I think it should be, so all my screen and the audios are recorded and I'll post on the YouTube. Okay. Okay, so let's continue our discussion on the moment-generating function. In short, we write the MGF last time. Okay, so last time we showed that the first order derivative, so here I just use a prime for the derivative, and then the subscript x for the random variable that I'm working with, and then the parenthesis t is that this is a function of t. Okay, so we show that this is equal to the, okay, so when we set t equal to 0, this is equal to the first moment, which is the expectation. And then we also make another comment, which is the kth order derivative for the moment-generating function. This is equal to the kth moment here. Okay, so last time we showed that the first order derivative is equal to the expectation. So in today's lecture, I will first show that the second order derivative is also equal to the second moment, and then we will proceed from there. Okay. So last time we also have the expression that the moment-generating function can be expressed as an infinite sum. So what we have is the summation of the 1 multiplied by p of x plus the summation for all the x's, tx raised to the power of 1 factorial px. So here I'm just copying down what we have written on the blackboard on Tuesday. So we need this expression again for some subsequent result. So I just need to copy paste again. But you already have this in your notebook from notes from last time. And then this is an infinite sum. Okay, so last time we take the first order derivative, and then we show that it's equal to the expectation. And then the first order derivative is the following. So the first term here does not involving t, so when we take derivative, ends up with a 0. Okay, and then for the second term, there's only one t involving, so we have the sum over x multiplied by p of x. So up to this point is still the result from last lecture. So for the second term, when you take the derivative with respect to t, you will have x squared over 2 factorial, and then multiplied by 2t p of x. So again, I want to emphasize that this is a function of t, so when you take the derivative, you take the derivative with respect to t, not x anymore. Okay. Similarly, for the third term, you have x raised to the power of 3 over 3 factorial, and then 3 multiplied by t raised to the power of 2 multiplied by p of x. That's the first order derivative for the fourth term here. Okay, so this is what we have from the last lecture. Okay, so what is new today is that we're going to take a second order derivative and show that when t equal to 0 is equal to the second moment. Okay, so from here is what is new from last lecture. Okay, so I'm going to use double prime to show that I'm going to taking a second order derivative or another derivative from this line here. Okay, so can someone tell me what is the derivative for the first term here? Just 0, right? Okay, what about another derivative with respect to t for the second term here? Also 0, right? That's not involving t. Okay, we have t, 2 zeros here. What about this one here? When we take the derivative with respect to t for the third term, What does it equal to? Yeah. So essentially just the t is gone, right? And then we have the 2 factorial. You guys know what factorial is, right? Just like the, yeah, okay. So that it will cancel out with this 2. So that means we only have the x squared p of x. Is that what you saying? Yeah, thanks. Okay, what about for the 4th term, taking the derivative, another derivative, what does that equal to? T times x cubed. Yep. Do you agree with that? Okay. T times x cubed, and then p of x. Okay, and then again infinite sum. And here I just want to emphasize that for all the terms that after this the 4th term, they all involving a t. Do you agree with that? Because they all raise to some higher order as the power. So when you take another derivative, you're still having some t involving in the following term. Okay. So this is the 2nd order derivative from the moment-generating function. And again, it's taking a derivative with respect to t. Okay, so now let's set this t equal to 0. Let's check what does this equal to. So the first 2 terms is still going to be 0, right? And what is the result for the 3rd term here? So we are setting this expression for t equal to 0. What is the 3rd term equal to? It's just itself, right? Yeah. So x squared multiplied by p of x. What is the result for the 4th term here? 0, right? What about the 5th term or all the other terms? All zeros, right? They're all involving t. But right now we set all the t equal to 0. So all the terms after the 3rd term, they all become 0. And then the first 2 terms are also 0. So what does this equal to by definition? This is just the 2nd moment, right? Okay, yeah. So here you can repeat the same process for the kth order derivative and set t equal to 0. You will get the corresponding kth moment. Okay, yeah. So in the last lecture, we showed that the 1st order derivative for the moment-generating function set t equal to 0, that is the 1st moment. And then now we just show that when you take a 2nd order derivative, set t equal to 0, we have a 2nd moment. Okay, and then, yeah, so if you want higher order moments, you just take the corresponding order of derivative for the moment-generating function, set t equal to 0, you'll get the corresponding result. Okay, so that concludes the introduction of the moment-generating function. Is there any question or comment so far before we proceed to some examples? So let me just emphasize again, this is the result that we talk about. If you want the kth moment, just take the kth order derivative and then set t equal to 0. I think here I should be more precise. This should be when t equal to 0. Okay. Yeah. So here we show that the 1st order derivative, t equal to 0, is 1st moment, 2nd moment, and then if you want a kth moment, just keep taking derivatives. Any question or comments? Okay, so now let's proceed to some examples. And yeah, so I think in last lecture, we also used the definition of the expectation to calculate the 1st moment and the 2nd moment for the exponential distribution, right? And then, okay, so let me write it down. So in the last lecture, we work on the exponential distribution. So x following an exponential distribution with parameter lambda. We know that the x, the support, is greater or equal to 0, and the parameter lambda also equal to 0. Can someone also just tell me what is our result from last time? What is the expectation for the exponential distribution from last time? The one in your notes. 1 over lambda. Yes. So we use the definition of the expectation to show that it's 1 over lambda. What is the second moment?
2 over lambda squared.
2 over lambda squared. Okay, so these are the results that we derived. We kind of like used the whole blackboard to show these results last time, right? Okay, so today or now, I'm going to use the method of the moment Jenny function to show the same thing by taking derivative and then set t equal to 0 to see if we can still get the same result instead of going all the works on the blackboard like last time. Okay, so that is what we're going to do now. Okay. So here is the density function that we also have from last time. So the lambda e of negative lambda multiplied by x. Okay. So first of all, we need to derive the moment Jenny function for an exponential distribution. Okay. So can someone remind me what is the definition of the moment Jenny function? Yes. Yeah. So expectation e raised to the power of tx. Okay. So now we are going to derive the moment Jenny function for the exponential distribution. So let's proceed. What is the definition for the expectation now?
The argument times something else.
The density function, right? Yeah. So this is your g of x multiplied by the density function, and then we have the following. Okay, so now let's continue to derive the moment Jenny function. So let's see. First of all, we can combine the term that has the power involving x together. Okay, so we have the following. So the integral, and then the lambda, and then I'm going to use the longer expression, the exp expression, instead of the power thing here. But essentially they're the same thing. Okay, and then using the square bracket, negative, and I'm going to write in this way. So lambda minus t multiplied by x, closing the square bracket, dx. Do you agree with that? I'm just grouping the things together. Yeah. So I'm just grouping the power for the tx and the negative lambda x into one expression. Okay, so next we just need to evaluate this integral and then come up with an expression, and then that final expression is the moment Jenny function for the exponential distribution. Okay, so any thoughts on how to work on this integral here?
Can't you just integrate it directly?
Yeah, but it might get a little bit complicated. Yeah, that could be one option. Yeah.
And just keep producing copies of the inside of the.
Sure. Yeah, there could be many ways to work on it. Yeah. So okay. Yeah. I just want to pause and to let you guys to think about it when you're looking at some expression, so that when you're working on exercise, you can also think about it. So in this, so we have solved some integral using like integration by parts. So in this one, I'm going to use some other methods, so that kind of like also like presenting some other ways for you to work on it. Okay, so I'm just going to use the simple change of variables. So here I'm going to set u equal to the things that inside the square bracket, or particularly lambda minus t multiply by x. Okay, so if I change the things inside the square bracket with the u, then I can also write x is equal to 1 over lambda minus t multiplied by u. And this also gives me that dx is just equal to 1 over lambda minus t du. Okay, so I'm just going to use the change of variable to work on this integral for this exercise. Any questions so far? So what we have done so far is that this is the momentary function. We use the definition, write it as the expectation. And then we also use the definition of the expectation, write it as the integral. And then we see that this is the integral that we want to work on it. And then we choose some other tools, some other tricks. For example, last time we used integration by parts. This time we use like the simple change of variables to continue to work on this integral. Okay, so next let's plug in the terms that we have here inside the integral. Okay, so we have the lambda here, and then exponential of that after the change of variable, it's just the exp negative u. And then dx, we are going to write it in this way. So we essentially just have a 1 over lambda minus t, a constant, multiplied by du. So you can see that for this trick here, after we make the change of variables, what we end up with is just some constant multiply. So let me bring the constant outside. And then we have the integral of negative u du. So by change of the variables, we kind of like reduce this problem into a relatively simpler problem. Okay, so now what is the integral of the exponential of negative u? Sorry?
Negative u times the exponential of negative u.
Can you say that again?
Negative u times the exponential of negative u.
Okay, so if you want to check whether that result is correct or not, you can just take the derivative of that expression and then see if you can get that. So I'm going to say that the result is the following: negative exponential of negative u. So you were saying there's another u in the front, right?
Awesome.
Okay, so if you want, you can double check that expression, taking derivative with respect to u, and then if you can get this result. So we can also verify this. So this expression, I'm claiming this is the integral of that. So let's take the derivative and see if we can get this. So when we take derivative with respect to u, there will be a negative sign in the front, so cancel out, there will be positive. Exp of negative u become itself, so I think this will be the integral of that. Okay. Now we have the final expression. We just need to evaluate the integral from the lower bound and upper bound. So what is the lower bound and upper bound here for exponential distribution?
0 and infinity.
Yes, but that is for x, right? Here we are evaluating the integral for u after the change of variables. So what is the lower bound and upper bound for u? Okay, so to answer that question, let's take a look at how we define u. Okay, so we define u in this way. We know that x is ranging from 0 to infinity. Then can someone tell me what is the lower bound and upper bound for the corresponding u? So when x equal to 0, what does u equal to? 0. When x equal to infinity, what does u equal to? To infinity, right? Okay, so although u ranging from x ranging from 0 to infinity, we need to consider u. But in this case, u also ranging from 0 to infinity. But my point is that you want to make sure you are talking about u, not x anymore, after you change the variable. So it depends on the trick that you apply. So if you do integration by part, you need to make the corresponding argument for different tricks. So here we're making a change of variables. You need to make sure that your range, the upper bound, lower bound is for u. Okay, it might be different if you do different type of change. So in our case, it's also just ranging from 0 to infinity. Yeah, but make sure that you double check what are the random variable that you are working on. Okay. Does that make sense? Good. Okay, so now let's evaluate that. So we have lambda over lambda minus t. And let's see, how should we write it? Let's write it in a fraction then. We have the e of u in the denominator and -1 over that. Okay, so I'm just going to, so whenever I want to evaluate this, for me, I like to write it in a fraction. Okay, so let's write it in this way. Okay, so what is the result for the square bracket here? So when we plug in infinity into u, what does that equal to? When we plug in 0, what does that equal to? Sorry? -1, right? Okay, so don't forget this is minus a -1. Okay. So our final result, which is also a function of t, just to reiterate again, is lambda over lambda minus t. And do you guys still remember what is this expression stands for in our examples? Yes, the moment generate function for random variable x, where x follow exponential distribution, and this is a function of t. So you can see that there's a t showing up on the right hand side. So this is a function of t, and this is the moment function for x that follow an exponential distribution. Okay. Any question, comments up to this point? Okay. Now okay, so before that, let me just make some other manipulation to re-express this term here. Okay, so it's really up to your preference, and then there are different ways that you can write the same fraction. So this expression here can be also written in this way. Do you agree with that? Yeah, so I just write it, instead of fraction, I want to write it as a product. Okay. There are some other ways, and I can also write it in this way. 1 minus t over lambda, altogether raised to the power of -1. Do you agree with that? So one way to see this is that you can think of 1 as lambda over lambda. So you will have lambda in the denominator, and then lambda minus t on the numerator, and then you take the inverse, you will get this expression back. Okay. So here I'm just showing 3 different ways to express the same thing, and then which one you want to use is really up to your application. Okay. So I'm going to use maybe like any of the 3 terms based on my needs. Okay. But they are essentially the same thing. Yeah. Any question or comments? Okay. Next, let's answer our question regarding the expectation and the second moment. So for the expectation, we just make the claim that this is the first order derivative set t equal to 0. So now, okay. So now what we're going to do is that we know that this is the momentary function for exponential distribution. And now let's take the derivative with respect to t, and then let's see what does that ends up with. Okay. So in taking the derivative, which expression do you guys want to use? Which of the three here you guys think would be easier for taking derivatives? Middle one. Yeah. So I'm also going to use the middle one to take that derivative. Okay. So to take the derivative, this is a function of t, so we want to take the derivative with respect to t. So I'm going to use the second expression for taking derivatives because I think, and also you think it's easier, right? I also think it's easier for the second term. Okay. So can someone tell me what is the first order derivative for the second expression here with respect to t?
Lambda divided by the
Okay, so so we have a lambda. You're saying lambda in the front. Okay. Well, next. Okay. What else? Yeah.
negative lambda, so because we're starting with the power rule.
Okay. So let me write it as -1 and a parenthesis. Is that okay? Okay. I prefer to write it in this way. Okay. What are some other terms here?
And then parenthesis lambda minus t.
And then
To the -2.
2, right?
And then
What
chain
else?
rule, so it's times -1 again.
Why is that?
Because inside you have -t and you need to take
The chain rule, right?
Yeah.
The negative. Okay. So do you agree with that? So I'm going to using the second expression because I think it's easier to taking derivative. And then I claim that this is the first order derivative with respect to t. Do you agree with that? Okay, so now let's simplify that. Let's see. The -1 and -1 cancel out. That means we have lambda over lambda minus t raised to the power of 2. Okay, so now I'm going to using the fraction term expression again. So I'm changing the representation or the notation again. Okay, so this is my result. Do you have the same thing? Okay, so when we evaluate the first order, when we evaluate the expectation, when we want to calculate the expectation, what should we do next? There's one thing. When we take the derivative, what else we should do here? Yeah, set t equal to 0. Okay, so don't forget, after you're taking the derivative, don't forget to set t equal to 0. Okay, so when set t equal to 0, what does this equal to? Okay, let's say lambda over lambda squared for now, and then 1 over lambda, right? Okay, so this is what we derived in the previous lecture, right? So we have the same conclusion. So what we have done so far is that we first used the definition of expectation. We have done using the whole lecture, the lecture on Tuesday, to get the result for 1 over lambda. And today we have used a second method, which is called a momentary function. And then you can see that we just actually use a few lines, relatively easier, and then first derive the momentary function, taking the derivative, set t equal to 0, we get the same conclusion. So this is essentially offering a second method to calculate the expectation. Yeah. So it's up to you whether you want to use the method that we did on Tuesday or the method that we did on today to calculate the question.
Is there any way to determine which way would be easier or more efficient?
You only know which way is easier after you try both.
Okay.
Yeah. So I think, yes, I think for exponential distribution, it's maybe the momentary function is easier, but there are some other distribution, maybe the definition is easier. Yes. Okay, so we can see that by using this method, we have the same conclusion as what we did on Tuesday. Next, let's continue for the second moment, and let's see if we get the same result from Tuesday. Okay, so to get the second moment, what should we do now?
Take the derivative that was on in the last question.
Okay, so take a second order derivative of this expression, or this expression also works. Okay, so let's take the derivative for this one. So I'm going to, you can see that for taking derivative, I usually like to use the multiplication for. But when I evaluating the things, I want to use the fraction for. Okay, so now I'm switching back to the second expression. So like this kind of framework I want to use when we're taking derivative, and this is the kind of the expression that I want to use to taking when I evaluating something. Okay. So I'm using the second expression again here instead of fraction. Okay, can someone tell me what is another derivative for this expression? Let's read it term by terms. Yeah. So we have yeah, go ahead.
You bring the -2 down.
Okay, so let me bring the lambda first in the front. Okay,
Lambda,
okay, and then -2.
-2
Okay,
times lambda minus t to the -3rd power.
mm-hmm.
And then now you take the derivative from inside the parentheses, yeah.
-1. Okay, thanks. And then I should have a form that look like, so okay, now I'm going to using the fraction form again because we want to evaluate something, so I want to change it to fraction. Okay, so for the numerator, we have the 2 multiplied by lambda, and then for the denominator, I have the lambda minus t raised to the power of 3. And then we want to evaluate this at t equal to 0. Okay, so don't forget taking the derivative first, and don't forget to evaluate t equal to 0 afterward. What does this equal to when we evaluate at t equal to 0?
2 over lambda squared.
Okay, so yeah, 2 lambda, and then lambda raised to the power of 3, and then that means 2 over lambda squared. Okay, is this the same result that we did on Tuesday? Okay, yeah. So you can see that kind of like a substantially reduction of work to calculate this. So on Tuesday, we used the whole lecture to calculate these two things. But right now, we just use homogeneous function, and then we directly get that. Okay, and now let's just, for completeness, the variance of x for x following exponential distribution. This is the second moment. So lambda that minus 1 over lambda square, and that is 1 over lambda square. So this should be the same thing that we have on Tuesday. Okay, yeah. So I think it will be relatively easier in calculating these two terms. Any question or comments? Yes.
Do the negatives just all cancel out? That's why it,
Which part? Which negative?
the negative to the power 3.
Oh, I put it so this is what I meant by this is the multiplication form. So what you mean to here, right?
Yeah.
Yeah. So when I put it in the denominator, that would be the.
Oh right, never mind.
Yeah.
Sorry.
So that means that it's the thing raised to the power of 3 and then in the denominator. So
Right.
yeah. So here is the multiplication form. This is the fraction. So depends on the needs, and then I change. Yeah.
And then the -1 and -2.
Cancel out to this.
Right.
Two.
Thank you.
Yes. Good question. Thanks. Any other question or comments? Yes, yeah, go ahead.
So the reason why you rewrote the moment generating function like 3 different times is just to
Oh.
say that your derivative would be easiest?
You mean this line here?
Yeah.
Yeah, it just depends on which one you want to use. For example, I use this expression when I take derivative. I use the fraction form to when I want to evaluate something. And later you will see this expression is also useful for something else. Yeah, but they are all equal, right? The equality holds. Right? I just rewriting as a different form. Yeah, good question. Yeah. So later I will comment a little bit on the reasoning for this expression. We haven't used it so far, but they are the same, which is the moment generating function for the exponential distribution. Okay, let's see. So in the lecture notes that I post on Canvas, I also have a binomial distribution. Yeah, if you're interested, you can take a look at that, but I don't think we have time for today to evaluate that, so I think I will skip that examples. And yeah, can someone remind me, did we do the Poisson distribution on the first week? Through the expectation, right, on the blackboard as a, I think we.
I'm pretty sure we did.
Sorry, what?
I'm pretty sure we did.
We did it, right? Okay. So I want to circle back to use the moment generating function method to do the Poisson distribution again to see if we get the same answer. Okay. So basically, we are doing the same thing by using different approach. And then what we're going to do is to verify if we get the same thing. Okay, so that would be, that is what we're doing here. So I want to revisit the Poisson distribution now. Okay, so x following a Poisson distribution. And I think I use lambda as a parameter. And then, okay. So what is the support for Poisson distribution? All the natural number including 0, right? And then for lambda, parameter greater than 0. That's what we have from last week. And can someone also take a look at your notes on last week? What is the expectation that we have from there? Lambda, okay. Did we do the second moment? What? Second moment is equal to, can you say that again? Lambda?
Lambda squared plus lambda.
Lambda. Okay, so that means the variance is also equal to lambda. Okay, so these are the 3 results that we derived on week 1. So right now, we are going to use the method, the moment generating function, to derive the same thing, and then let's see if we get the same result or not. So again, on last week, we also do the whole blackboard thing to derive all the 3 results using the infinite sum, that kind of tricks. But now, let's derive the moment generating function, and then taking derivative, and see if we get the same result. Okay, so now let's derive the moment generating function for Poisson random variable. Okay. Can someone tell me what is the definition for moment generating function for a discrete random variable?
It's the same as the continuous, except it's a summation instead of an integral.
Okay, so just change it to summation, right? Okay. So first of all, let me write down, this is an expectation E of tx. So that is the definition for the moment generating function. Okay, and then for the discrete case, we just don't need to work with integration, just need to work with summation. And then your function gx is just E of tx multiplied by the probability mass function. Okay, so the probability mass function for the Poisson distribution, lambda raised to the power of x, e raised to the power of negative lambda, and then x factorial. Any thoughts on how to work on this summation here? Also an infinite summation.
Can you combine the x terms?
Mm-hmm. Yes, that will be one component. Okay. Yeah. So let's simplify this expression now. So what is considered as a constant here?
To the negative lambda.
Yes, exactly. So now we are working with x. So again, the momentary function is a function of t. But when we write it as the expectation, so you can see that the summation is working on x. So now anything that does not involving x is considered as constant. Okay. So the e raised to the power of negative lambda is a constant. Okay. And then we have the summation over all the x. And let's see how we can group these things together. Okay, so now we have the e of tx and then the lambda of x, and then let's group them together. Okay, so I'm going to group them in the following way. Lambda multiplied by e raised to the power of t, and then all together raised to the power of x. Do you agree with that? Okay, and now by looking at this expression, does that remind you of something that we have seen before? And then what can we work or substitute this expression with? So this is an infinite sum, and then we have seen something like e raised to the power of x is equal to n equal to 0 to infinity, x raised to the power of n, and then n factorial. So this is what we call equation to use last time. So we are going to use the same trick here. So now by looking at this expression here, so let me underline the expression here. So now we are going to use this, the right hand side of this equation to replace this term here that I underlined. So can someone tell me what does the term reduce to? So I'm going to use the right hand side of this one, the one that I underlined here, to replace the expression for this one. So this one is also summation of 0 to infinity. So now, what do you think I should replace this expression with? By looking at this known result.
E to the lambda times
E to the, okay, yeah. So here, the x is the thing that is in the parenthesis, right? So in our case, the x in this expression will be the thing in the parenthesis.
Right.
So we just write e with whatever inside the parenthesis. Replace the x in here, right? Okay, thanks. Let's see. I'm going to write it. Okay, then I will write it in this way. E t. So this is okay. So this is e raised to the power of lambda multiplied by e, and then again raised to the power of t. Okay. Yeah. Let me know if this notation, if it is unclear. So do you agree with that? The one that I underlined here is equal to that. Do you agree with that? So this is so let me reiterate again. This is the momentary function we want to evaluate. And then we come up with this term. And then we see that there's an infinite sum, and then we know this is a known result. And I'm going to use the expression of this to replace this part, and then we end up with this one. Do you agree with that, or if you have any question or comments? Yes.
Could you just show us how you get that from that?
Sure. Yeah. Let me first complete this equation here. So there's also another constant. So let me bring that in the front. Okay. So now this equal sign is complete. Okay. So the question is how to get this to here, right? So what I'm claiming is that the part that I underline is equal to this based on this result. Okay. So here, okay. So maybe let me use as a side notes. Okay, so we can see that the resemblance of these two expressions. So we also have the summation of 0 to infinity. Okay, so here I'm going to set this x become here, this lambda e raised to the power of t. And I'm going to set this n to the x here. Although this can be a little bit like a confusing, but I hope that you know what I mean by recognizing this. Okay. So this is a known result here. And I'm going to set the thing that I put in parentheses, the lambda e raised to the power of t. I'm going to call that my x for this expression. And I'm going to call the power and the factorial x, I'm going to call that the n in this expression. So all I need to do here is that I'm going to use the term, these terms I define on the left-hand side. So e raised to the power of x, and then we define x as this. So we just bring this part to this x here, we have e with x. Does that?
Right. So you redefined what x.
This is not they're not equal. I'm just like assigning. If you want, okay. So maybe I can make it a little bit clear in another way. Okay. So just to avoid any confusion. Okay. If I write it in this way, do you? Let's see if you agree with that. So e of y is equal to y raised to the power of n and then n factorial. And then I'm going to set let's see. I'm going to set this part, I'm going to call y. And I'm going to call this x to n. And then, so this part, I'm going to call it y. And then the x, I'm going to call it n. And plug into this y and n here. So you just have e and e to the power of y.
Gotcha.
And the y is this one. So e of the y is just e of this. Just like changing the terms. Yeah. Yeah, good question. Any other question or comments? Okay, next let's continue on simplifying the result here. Okay, so I'm going to simplify this expression in the following way. So e raised to the power of lambda et minus 1. Do you agree with that? I'm just combining, so lambda multiplied by that minus a 1 for this. And then this I'm going to claim is going to be the moment-generating function for Poisson random variables. Okay. Any question or comments? Next, to evaluate the first moment, second moment, let's take derivative. So e of x is equal to the first order derivative for t equal to 0. Okay, can someone tell me what is the derivative of this with respect to t? Yes, go ahead.
Wouldn't you take the entire thing that's on top of e, the lambda bracket e t minus 1, and put it in front of the exponential? Would you take the derivative?
Yes. Yeah, thanks. Okay, so now let's take the derivative of this. Okay, so first of all, itself should be involving in the term, right? So let's copy down one, so let's make one copy of itself. Okay. So itself should always appear as part of the derivative. Okay, now we are going to apply the chain rule for the power thing. That is what you meant, right? Okay, so what is the derivative for the power here? Okay, so it should be derivative of this part. So there should be a lambda as a constant has been plugged in, involving. And then for the second term here, so this thing here should also, I'm not sure if this okay. So we are taking a derivative for the power, and this is considered as a constant. So we bring it outside, and now we take the derivative of the thing in the parenthesis, and that gives us another e of t. Do you agree with that? Okay, so what we're doing here is that we want to take derivative of this with respect to t. So first of all, itself should be appearing in the derivative. So we make one copy of itself. And then we take the derivative for the power term, for this power. Okay, and then the lambda here is a constant. So then we have a lambda in the derivative. And then we take the derivative for the terms in the parenthesis, and then we have this itself. And then if you want to be more rigorous, you have to take the power for the t. It's just equal to 1. So then if you want, you can multiply by 1. But essentially, this is the first order derivative from this. Do you agree with that? Any question for the first order derivative? Okay, what should we do next after we take derivative? Yes, t equal to 0. So don't forget t equal to 0. So can someone tell me when t equal to 0, what does this equal to? Okay, so let's take a look. So for this one here, when t equal to 0, we have e raised to the power of 0. That's a 1. Minus a 1, we have another 0. So the whole thing goes to 1. And then we have a lambda for the second term. E raised to the power of 0 is still a 1. So in the end, we should have a lambda. And this is also the same result that we derived in the first lecture. The first moment or the expectation for a Poisson random variable is equal to lambda. Any question? Comments? So again, on last week, we also use the definition of that. We do lots of change of like the j equal to something x minus 1. We do lots of tricks just to get the lambda. But today, we derive the homogeneous function, taking derivative, and then we directly get the result for lambda. So we're just doing the same, we're just getting the same result, but by using different methods. To me, also for Poisson random variables, not using homogeneous function is simpler. Okay, there's no other question. Let's take another derivative. The second order derivative will be a little bit complicated because we have two terms that are involving t. So we need to use the product rule here. Okay, Can someone tell me how to take the second order or another derivative from this expression here? Yes.
Yeah, well, I combined it into one thing to make it easier to work with.
How do you combine it?
Oh, I just did plus t at the end of that.
You mean combine, bringing this t into
Yeah.
here? Okay. Then do you still need to use chain rule? Product rule.
No, you don't need to use product rule. It's just chain.
Okay. I don't have the. Okay, let me try. Okay, let's think about it. I don't know. I don't have the result, but let's try. Let's try.
I got the same results.
Sorry, what?
I got the same results.
Perfect. Then okay, let's do it that way. Let me try. So now I'm doing it from scratch. I don't know because it's very likely that I make some typo. Okay. So first of all, we want to do this. So we want to take another derivative for this expression, and based on your suggestion, grouping the t together. So that means I have this one. Wait a second. So if you group the t together, and then you still have the lambda outside the parenthesis, or not?
I like distributed the lambda, so it's like lambda times e to the
I see. Okay.
minus lambda plus t.
So do you mean you have the following minus lambda plus t?
Yeah.
Okay, and then you only left with a lambda, and then you want to take derivative of that. Okay, so you have this expression, right? Okay, so now let's take the derivative for t. That means you have, first of all, itself, right? Minus t, minus lambda minus t. And then yes, thanks. And then I put the lambda in the front, and then apply the chain rule for this one. So that means we should have lambda multiplied by et. Let me minus 0 and then plus 1. And then that's it, right? Okay, thanks. Thanks. Yeah. And then let's see how we can group these together. We will have lambda e raised to the power of lambda e.
I just plugged in t to the 0.
Oh, you okay, okay. So
It's kind of easy because we already have the first part.
okay. I just want to be more like a step by step. So for on notes. Okay. Yeah. Let's see. Yeah. Yeah. Okay. I haven't tried this way before, but it seems like it's easier than what I have on my own notes. Okay, I'll keep that. Yeah. Thanks. Et plus 1. Okay, so yeah, it does not change anything much. So I would just directly evaluate t is equal to 0, right? Okay, so let's see. That means we have lambda, and then e for t with 0. That's a lambda minus lambda plus 0, and then lambda plus 1. Okay, and that means we have lambda square plus lambda. Is that what you get? Yeah. Thanks. Okay, yeah, this way is more easy. It's easier, yeah. Otherwise, you will need to use the product rule. Yeah. Okay. Any question or comments regarding the second moment? So essentially, just take another derivative for a second order derivative and then evaluate t equals 0. Okay, and that means the variance of x is lambda square plus lambda minus the square of the first moment half lambda. Okay, so we verify the result that we derived on week 1 with the other methods. Do you guys need a break, or do you guys want to continue? Break? Yeah, then let's come back in 5 minutes. By the way, anyone is still trying to enroll in this class or are still on the wait list? Okay, so no one needs the permission code to enroll, right? Okay, good.
My notes got corrupted as you were like.
No, do you want to see anything?
I just wanted, yeah, it's from the.
Oh yeah. So if I scroll down to here, would that be enough for the notes?
No, I think it's up more.
Scrolling up, or
Yeah, it's up more.
this part? Can I? Oh, that's for the. Okay. That's for the previous example.
Oh yeah, for the.
Oh, okay. I will post this on Canvas. Just so yeah, because this is kind of like a. I think it chopped lots of are gone. So I'll post this and then on Canvas.
Alright, thank you.
Yeah.
So this is your first teaching?
Yes. Yeah.
This website where you like list out your research interests as well as
Oh, yeah, yeah. Uh-huh. So you want to like seek for some research opportunities? Yeah, sure. We can. Maybe we can talk about it after this class, or if we don't have time, we can talk about the office hour. Yeah, because for professor, everyone's doing research, so there will be lots of research opportunities. So yeah, we can talk about it. So maybe after this lecture, we can. This is like a 5-minute break. So after lecture or office hour. Yeah.
It's on your
So yeah, like maybe the canvas will be better. I forget it. Yeah.
Does this automatically pause the distribution?
Yeah, so the x here is y minus x. So this n is this x. Now, I know this is not yet because like using the notation, but this n is just index. But if you think about this as n, and you think about this as y here, like what I maybe the part here is
So this does apply to this one. So the x always x is 0 to infinity. So if I set x equal to n, then we have the same y. If I set y to n, then we have the right hand side. It's no longer for that. Oh, so you said x to 0, so that
It wasn't painful, it was just weird to do.
no, x is already 0. I mean, x is 0 from the finish.
Self-conscious about it, like I went to school and like middle school, yeah, like what is that? And I'm like,
It's already 0. Oh, right. Okay. So what I'm doing here is that I call x and call x as n here. I call the thing in the parentheses as y here. So I get the change in the notation. They are the same thing. Just change the notation. I call this one a y. I call it x to n, and then we will see that essentially these are the same thing. I can write this as the left hand side.
yeah, that's why I did it. Oh, yeah, so
He said not to turn it in late because you never know what's happening.
Yeah.
He said don't do that.
Okay, so is it 5 minutes already? I'm wondering, have any of you enrolled in 132 in 4/4? I feel like I've. No, never mind. Don't worry about it. Okay, so now let's talk about some other distribution. I think this is also involving in the in homework 1. Okay, so this new distribution, I'm not sure if you have heard of it, it's called the gamma distribution. And then I'm going to use the notation, the Greek letter gamma. And this is a continuous distribution with 2 parameters, alpha and beta. And then for the support, for the gamma distribution, also greater than 0, the parameter alpha beta also greater than 0. Have you guys heard of a gamma distribution before? Okay, so we were going to play around with this distribution. Okay, so for the probability density function of a gamma distribution, and then if you want, you can also put the alpha beta in the parenthesis. It's up to your own preference. And then I'm going to use this expression for the probability density function. So in some of the textbook, it might look a little bit different, but essentially they are the same. But for me, or for this lecture, I'm going to use this, this expression. Okay. So I think if you Google gamma distribution, you would see 2 types of expression. They are essentially the same thing, but it's just I personally prefer to use this notation or this form of a probability density function. I think the other version is just they set the beta into 1 over something, and then they write this as lambda multiplied by x, and this is a 1 over lambda raised to the power of alpha. It's just a notational thing. But for me, or throughout the lecture, I'm going to focusing on this expression. So just in case, if you see something that is different from this, they are essentially the same thing. It's just they use a different notation. Okay, that's what I want to emphasize. I think on Wikipedia you will see both of them, but I'm going to using this one of them. I'm going to use this version. Okay, so that's the probability density function, PDF. And then, so for this one, the numerator here, sometimes people call the kernel function. And then for lots of the times, whatever in the denominator is called the normalizing constant. And this is the reason when you take the integral of the PDF, they sum up to 1. So if you take the integral for the numerator, you will end up with the denominator. That means if you take the integral of the whole thing, it will sum up to 1. That's the meaning for the normalizing constant. So you divide it by that, and then when you take the integral, so that the probability will always sum up to 1. So that is the purpose of the normalizing constant. Okay, so that's that. And then another thing I want to mention is that this here is a naming thing. It's referring to like a gamma distribution. And this one here, so gamma distribution, I use 2 parameters to refer that as the name of the gamma of the distribution. So it's called gamma distribution. And here, the one that I put it in the denominator here, this is called a gamma function. Okay, and then a gamma function has the following definition. So this is a function of alpha. So if you input the alpha, it will give you a value. And this function is defined as an integral. Also, let me use y equal to 0 and y go to infinity. And then y raised to the power alpha minus 1, and then e raised to the power of negative y dy. So you can already see it's very similar to the numerator here. But this is the definition for the gamma function. Okay, so again, this is the name of the gamma distribution. It takes two parameters to define your gamma distribution. The things in the denominator in this PDF is the gamma function. Okay, so let me use a lowercase. So the gamma function is that when you plug in the alpha, the input here, it will give you some output. Okay. And then there are two particular properties for this gamma function. Is that, okay, so first of all, for this expression here, the alpha can be any real values or greater than 0. But for alpha, that is particularly in the natural number, I'm not going to draw the notation, but here I'm just going to say that this is for the natural numbers. Then you have the following two properties for the gamma function. So gamma of alpha, for alpha is a natural number, is equal to alpha minus 1 factorial. This only holds when alpha is a natural number, like an integer. And then if you want to evaluate alpha for real number, you need to use the integral. Yeah. But when alpha is an integer, it reduces to alpha minus 1 factorial. Another thing for this gamma function is that you also have the following. So gamma of alpha plus 1 is equal to alpha multiplied by the gamma function of alpha. Okay, so these two only apply when alpha is integer. If alpha is not integer, you should use the integral to evaluate that. Okay, question?
When you say like integer, you mean like when it's a discrete function versus when it's continuous?
No, I'm saying, so the random variable here is x, and x is continuous. Here I'm talking about alpha.
Oh, alpha. Okay,
So alpha, no, it's not x. So x itself is still going to be continuous, but alpha is just a parameter. I'm talking about alpha, so not x. Yeah. Any question regarding like the settings for this gamma distribution? Yes, yeah.
I missed out. Was the normalizing constant the beta n to the power of alpha in the bottom, the entire denominator?
Oh, the entire denominator is called the normalizing constant. Yeah. So the numerator is called the kernel function. Just sometimes if you see some people talking about kernel function, yeah, and then that is the expression. And then the denominator, the whole thing is called the normalizing constant. Yeah. And then this is the gamma function. Yeah. And then just want to point out that this is a function that is just a name, but you can use gamma to rewrite that name.
But I'm just going to use some Greek letter as a short notation. Yeah, any other question or comments? Okay, next, let's play around with this gamma distribution. Okay, so first of all, let's take a look at the kth moment for the gamma distribution. Okay, so now I'm going to use the definition for the expectation to get the k to rewrite this expectation. Okay, so what is the definition for expectation for kth moment? It's just the integral for the function, and the g of x is just x raised to the power of k multiplied by the density function. Okay, so the density function is x raised to the power alpha minus 1 e negative x over beta, and then the gamma function of that dx. So this is just a definition for the expectation. Okay. So now let me ask the question, what is constant and what is random here? Yeah, but particularly more specifically for this expression, what are the constant thing that we can bring it outside the integral?
Whenever the gamma alpha,
Mm-hmm. And what else?
beta over
Okay, yeah. So this is considered as a constant. So I'm going to bring it outside the integral when I'm evaluating the kth moment. Okay. So that means we have the remaining term left inside the integral. So now I'm going to group the x together in this way. So I'm going to have x raised to the power of alpha plus k minus 1. And then exponential of negative x over beta dx. Okay. So just to reiterate again, we are trying to evaluate the kth moment, or the expectation of x raised to the power of k. We use the definition of the expectation, which is the right hand side, and we have this term here, and then we have the constant term, and then we move it outside integral, and then we group the things remaining inside the integral as the following. Okay. Anything we can do here to proceed to calculate the integral here? Any thoughts? How we can solve this integral, which seems to be a little bit complicated because there are two x involving. Any thoughts on how to work with this integral? Yes?
Could we multiply it by beta alpha over gamma alpha, and then again by the inverse to make it look like a
Distribution.
Yeah.
The goal is to, when you take the integral, that it becomes a 1, right? Yes, that's exactly what we're going to do. Thanks. Okay, so let's write down what she mentioned. Okay, so first of all, we have this constant. By the way, did you come up with that, or have you seen this kind of trick before?
We went over it in section.
Oh, we
Also-
already finished? Ah, okay.
Yeah, and also in 131.
Ah, great. Oh, so this is already done in 131.
Yes.
Ah, okay. Then maybe I can. No. Okay. Sure. Okay. Yeah, because. Oh yeah. Okay. So let's write down what she meant. Okay. So, I'm going to multiply a 1 in a way that I'm going to re-express in this fraction. Alpha plus k for beta alpha plus k divided by gamma alpha plus k beta raised to the power of alpha plus k. Is this what you meant?
Yes.
And then we have the integral. Okay, so after I finish this, I will just comment a little bit on what I'm doing here. Dx. Okay, so essentially what we're doing here, so let's start from the first line. We're trying to evaluate the expectation of the x raised to the power of k. This is the definition for the expectation. And then we come up with this term by plug in, or by bring the constant part outside the integral. And what I'm doing in the third line is that I'm multiplying by 1. And I'm going to express this 1 that I'm going to cover in the square bracket in a fraction form. So the same thing divided by the same thing is equal to 1. So I did not manipulate the term. So I'm just multiplying by 1, but I'm designing this 1 in a fraction form. So it does not, so the equation, the equal sign still hold. Okay. Any question or comments for the third line? Okay, so the reason why we are going to do that, why we're doing this, is the following. So for the fourth line, okay, so we have the gamma function alpha plus k multiplied by beta alpha plus k on the numerator that I multiply by 1, and then for the denominator I have gamma function of alpha beta raised to the power of alpha. So I'm using this denominator and this numerator come up with the first term here. And then I'm going to bring the denominator in the square bracket inside the integral, because that is a constant, does not involving x. So I can move wherever I want them to be. So I move it inside the integral. Okay, so here I have dx raised to the power of alpha plus k minus 1 e negative x over beta. So that's the thing originally inside the integral. And then I bring in the constant term from the denominator. Alpha plus k dot dx. Any question so far from the third line to the fourth line? Yes?
How did you know to do that?
By design. So the thing is that, yeah, good question. So now the reason why we want to do this one, right, the square bracket, is because we want to do it this way. And from here, by looking at this expression, what do you think this integral should equal to? It's just equal to 1, because this is the probability density function of a gamma distribution. Okay, so here is the PDF for gamma distribution. It looks like this. So now if you think about this alpha as alpha plus k, so then this alpha becomes alpha plus k, this alpha becomes alpha plus k minus 1, then essentially you will have the same thing here, the thing inside the integral. So I'm claiming, or I'm saying that the thing that I'm underlying here, this is a probability density function of gamma distribution with the parameter alpha plus k and the beta, after I bring in the denominator inside that, right? And then the integral of the probability density function for all the support, like 0 to infinity, should equal to 1, right? So then to answer your question, why we want to introduce the 1 in this form is that we want, when we plug in the denominator inside the integral, this becomes a density function. Then the density function, when you take the integral, is just equal to 1. So that's the reason why we want to design that in this way. So this equal to 1. Okay. And for the integral part that is equal to 1, that means the whole expression just reduced to this fraction. Alpha plus k divided by gamma function of alpha, and then like that. Okay. Any question or comments?
Could you show one more time how the integral equals 1?
Oh, this is just the definition for the density function. So for any, let me put it here. So for any probability density function, so for x that follow a density function, integral of f of x is equal to 1 for all the x, when x is a PDF. This is just the definition for the probability density function. So
One simple case, let's think about the discrete case. Let's say if we roll a six-sided dice. Let's say we roll a fair dice, and then each of the probability for landing on 1 and 2 all the way to 6 is equal to 1, 6, right? And then if you sum over all the probability, in that case it's just equal to 1. That's for the discrete case. And here we're working with the continued case, so if you take the integral, it's just equal to 1. Yeah. So for the integral for any density, probability density function, always equal to 1. Yeah. Okay, since we have 5 more minutes, maybe let me complete the result. So here, what we start with is the expectation for x raised to the power of k. So another result for the gamma distribution is that the kth moment is equal to beta raised to the power of k of alpha plus k gamma function of alpha. So this is another result for the gamma distribution. Okay, so now, so that means the kth moment for a gamma random variable has a, let's say, a closed form expression. So we can easily find out what is the first moment by setting beta equal to 1, by setting k equal to 1, gamma function of alpha plus 1 of gamma of 1. This is equal to beta of alpha multiplied by the gamma function of alpha. This is, again, we apply the property that we introduced earlier, divided by gamma function of alpha. So that means the expectation of a gamma random variable is just alpha beta, the product of the two parameters. Okay, so let me write down the result and then let's discuss more about that. So for the second moment, similarly, let's set k equal to, so here's set k equal to 1, this is set k equal to 2, alpha plus 2, gamma of alpha. Okay. Anything that we can work with alpha gamma question? Comment?
Yes, for the expectation of x to the k, when alpha is an integer, could we reduce it to alpha plus k?
Say that again.
Oh, for that
This one.
general, yeah, that equation. Can we when alpha is an integer, can we reduce to alpha plus k? That fraction?
I still don't get what you mean by that. So these are the two things that applies or valid in the.
So using the first property, I guess it would be.
You want to use the factorial?
Yeah.
Okay, yeah, sure. If you want, you can use, yeah.
And so it would be alpha plus k minus 1. Is that what it would be?
Factorial.
Yes.
Yeah, alpha plus k factorial. Yeah.
Yeah.
Yeah, if you want, yeah. If alpha and k are both integer, yes, you can do that. Yeah, but here we didn't make any claim on they are integer or not. So I'm just going to use a general expression. Yeah. Okay, so I'm going to use the second property from the above. So here, alpha plus k, I'm going to write it as alpha plus 1 divided by gamma of alpha. Okay, so when we think about it, is that I call alpha star as alpha plus 1. So that gives me the numerator is alpha star plus 1. This is equal to alpha star multiplied by gamma of alpha star by applying the first rule. And then for the second rule, I think the first rule is enough.
this is equal to alpha plus 1 raised to the power multiplied by gamma function of alpha plus 1. Does it make sense? So here we want to evaluate gamma function of alpha plus 2. So I write it as alpha plus 1 plus 1. And then I call this alpha plus 1 a alpha star. And then I can just apply the, so let me give them a number so that it will make it clear. So this I call it 1, this I call it 2, the 2 results. And then what I'm applying here is result 2. Okay, so that means the second moment here is equal to beta raised to the power of 2 gamma alpha plus 1 multiplied by gamma function of alpha plus 1 divided by gamma function of alpha. Any question for this part?
Sorry, what's the alpha star mean?
Alpha star is equal to alpha plus 1.
Gotcha. And then I want to apply the second rule that I introduced, that I mentioned above. So, what the thing is that I want to evaluate second moment. I plug in k equal to 2, I get this, having this. And then I want to call this alpha star, and then I know that the gamma of alpha star equal to that, and that will reduce to this.
Just again, change of some notation. Let me finish this line, and then I'll finish it real quick. So give me one more second. Beta star alpha plus 1 alpha multiplied by that divided by that. So alpha beta square alpha minus 1. That's the second moment for the gamma random variable. Yeah. Okay, so my point here is that for gamma random variable, there's a closed form expression for the kth moment. And then if you want to find the first moment and second moment, just set the k equal to 1 and 2, you will get the result. Set k equal to 1, the expectation is alpha beta. Set k equal to 2, the result is alpha beta square alpha, or if you want there, you can keep expanding. Yeah. So the point here is that the gamma random variable has a closed form expression for the kth moment. And then if you want the expectation, the second moment, just plug in k equal to 1 or 2. Okay. Yeah, I will pause here and then.
Isn't it plus 1? The last parentheses?
Yes, thanks. You mean, yes. Yeah, from here, the plus 1. Yeah, thank you.